Welcome back to this introductory lecture on proof techniques. In this seventh and last segment, we're introducing a new proof technique called direct proof for quantified conditionals. This will be the combination of two earlier proof techniques, namely the universal generalization and the direct proof technique. In this case, we're still interested in proving a conditional, but the conditional is universally quantified. In other words, the theorem we're trying to prove is of the form for all x, p of x implies q of x, which is often stated in English with a sentence of the form all p's are q's. So, we want to prove a conditional which is true for every possible value in the domain for x. So the standard way to prove such a theorem is to pick an arbitrary value in the domain of x, let's call that arbitrary value x bar, and to prove that p of x bar implies q of x bar. Once we have reached this point, we can prove the overall theorem by using the universal generalization rule to generalize over all the elements of the universe for x. So again, this is a combination of a direct proof technique for an arbitrary element of the domain and of universal generalization that allows us to prove a universally quantified theorem like this one. So as an example, let's prove our fifth and last theorem for this lecture, which is the following. For every integer n, if n is odd, then n plus 2 is odd. Notice that the dummy variable here is called n instead of x, but we do have a universal quantification here, p of x, which is p of n here corresponds to n is odd, and q of x, which corresponds to q of n here is n plus 2 is odd. So this is the theorem that we're going to prove to illustrate this new proof technique. Let's start the proof. First, we need to pick an arbitrary value in the domain for the variable. So let n bar be an arbitrary integer. I'm using the bar over the variable one more time here despite what I said earlier, just to make you comfortable with the fact that n bar is a specific but unknown integer. Now, we need to prove that p of n bar implies q of n bar. So what proof techniques do we have available to prove a conditional? Well, the first technique we saw was a vacuous proof. But for that technique to be applicable, we must prove that the hypothesis of the conditional is always false. Now, is p of n bar always false? Is it true that n bar is odd is always false? And the answer is no. So we can't apply a vacuous proof technique here. The second technique we saw was the trivial proof technique, which applies when you can prove that q of n bar is always true. So is it always true that n bar plus 2 is odd? And the answer is no. So we can't use a trivial proof technique either. So the third possibility is the direct proof, and that's what we're going to do. Remember that in a direct proof of a conditional, we assume that the hypothesis p of n bar is true, and we must infer that q of n bar under this assumption is also true. So let's assume the hypothesis p of n bar, namely, assume that n bar is odd. Remember, this is p of n. Well, if n bar is odd, by definition of being odd, there must exist an integer k such that n bar is equal to 2k plus 1. Let's add the integer constant 2 to both sides of the equality to obtain n bar plus 2 is equal to 2k plus 1 plus 2. Then we can trivially swap the order of the 1 and the 2 on the right-hand side of the equality to obtain the new equality n bar plus 2 equals 2k plus 2 plus 1. And that allows us to factor out the 2 in the two terms here, 2k and 2, to obtain the new right-hand side, 2 times k plus 1 plus 1. And the reason we did this is to obtain an expression of the form n bar plus 2 equals 2 times k prime plus 1, where k prime is simply a new name for the integer k plus 1. Again, it's important to argue that k prime is an integer, since we will need that in the next step, and that's easy to understand since from this step, which is where we introduce k, we know that k is an integer, and we know that adding 1 to an integer yields another integer. So k prime is definitely an integer, and therefore we can use existential generalization to infer that there must exist a case such that n bar plus 2 is equal to 2 times k plus 1. And a particular value of k that allows us to apply this rule is obviously the integer k prime. But this last proposition is actually the definition for n bar plus 2 being odd. So we can infer by definition that n bar plus 2 is odd. In other words, this concludes our direct proof, namely that by only assuming that n bar is odd, which is the hypothesis of the conditional, we were able to prove the conclusion of the conditional is also true. So we just proved the conditional for the particular value, the arbitrary value n bar. So all we need to do to conclude the proof now is to apply universal generalization to generalize the previous result to the set of all possible integers. So in conclusion, we just proved that for all n, if n is odd, then n plus 2 is also odd. And that was theorem 5. So this concludes our lecture on proof techniques. Make sure you are comfortable and remember and know how to apply these simple proof techniques in the rest of the course.